Good day everyone, this is the part 2 of Module 1 of CPA 208 Engineering Economics. So 5.0, the General Economic Environment. In broad terms, economics deals with the interaction between people and wealth, and engineering is concerned with the cost-effective use of scientific knowledge to benefit humankind. So, as engineers, we are going to manage that interaction for the benefit of people to consume the wealth in more or most economical ways. So 5.1 Consumer and Product Goods and Services. So under it is the consumer goods and services are those products or services that are directly used by people to satisfy their wants. For example is food, clothing, homes, cars, television sets, haircuts, opera. So opera is included here, and entertainment and medical services are examples. Okay, so under producer goods and services are used to produce consumer goods and services or other producer goods. So machine tools, factory buildings, buses, and farm machinery are example. The amount of producer goods needed is determined indirectly by the amount of consumer goods or services that are demanded by people. So those two are under the consumer and the producer goods and services. Next is the measures of economic worth. Goods and services are produced and desired because they have utility, the power to satisfy human wants and needs. So that's the purpose of it, goods and services. So they should have their utility values. Thus, they may be used or consumed directly, or they may be used to produce other goods or services. So utility is most commonly measured in terms of value, expressed in some medium of exchange as the price that must be paid to obtain the particular item. So utility is a measure of economic worth. It must be seen in the goods and services that uh, that are offered in the market. Okay, so as engineers, we should consider utility as a measure of economic worth. 5.3 Necessities, Luxuries, and Price Demand. So goods and services may be divided into two types, necessities and luxuries. So what are those? Obviously, these items are relative because for most goods and services, what one person considers a necessity may be considered a luxury by another. So it depends on the person. For all goods and services, there is a relationship between the price that must be paid and the quantity that will be demanded or purchased. So the price here is relative to the quantity. This general relationship is depicted in the next figure, figure 2-2, as the selling price unit, symbolized by a small letter P, is increased. So as the price unit increase, there will be less demand for the product. And as the selling price is decreased, the demand will increase. So the relationship between price and demand can be expressed as these linear functions. So price is equal to A minus B times demand. For 0 is less than or equal to demand, less than equal to A over B, and A is greater than 0, and B is greater than 0. So what is A and B? So A is the intercept on the price axis, okay? And B is the slope. So remember that A is the intercept on the price axis, and B is the slope. Thus, B is the amount by which demand increase for each unit increase in the price. So since B is the slope, it describes the rate, okay, of increase for each unit decrease in price. Both A and B are constant. It follows, of course, that the demand is equal to A minus the price over all over B. So B, or the slope, should not be equal to 0. So there should be a rate of increase or decrease. So now this is the figure. So in the y-axis, you have the price. In the x-axis, you have the units of demand. So you have the direct relationship between the price and demand. So general price and demand relationship. So note that the price is considered to be the independent variable, but is shown as the vertical axis. This convention is commonly used by economists. So this is the convention used by economists to compare price and demand. And they are considering price as independent variable. Because it is independent, because it is based on the company or the business entities who compute for the price of a product or service. 5.0 Competition. Perfect competition occurs in a situation in which any given product is supplied by a large number of vendors and there is no restriction on additional suppliers entering the market. So that is the occurrence of a perfect competition wherein the suppliers or the vendors are not restricted so that they have a competition. Under such conditions, there is assurance of complete freedom on the part of both buyer and seller. Why there is a complete freedom? Because of choices. Because the number of vendors increases, so the choices are. Okay? Choices of products or service. Next, perfect competition may never occur in actual practice because of a multitude of factors that impose some degree of limitation upon the actions of buyers or sellers or both. However, with conditions of perfect competition assumed, it is easier to formulate general economic laws. So here, we are just assuming a perfect competition. So monopoly is the opposite pole from perfect competition. Why? Because a perfect monopoly exists when a unique product or service is only available from a single supplier, and that vendor can prevent the entry of all others into the market. So when you say monopoly, an individual or one vendor only holds the or control a product or service, a unique product or service. So under such conditions, the buyer is at the complete mercy of the supplier in terms of the availability and price of the product because the buyer has no choice. So perfect monopolies rarely occur in practice. Because number one, few products are so unique that substitute cannot be used satisfactorily. So that is true. And governmental regulations prohibit these monopolies if they are unduly restrictive. Because our government or every government wants an equal opportunity for business individuals. So they don't prefer monopoly. Next is 5.5, the total revenue function. So the total revenue or the TR that will result from a business venture during a given period is the product of the selling price per unit or P and the number of units sold or D. Thus, the TR is equal to the price times demand, okay, or equals to P times D. So if the relationship between price and demand in equation 1 is used, so we will just substitute. So TR is equal to the quantity A minus BD multiplied by D is equal to AD minus BD squared. Okay? For this condition that demand is greater than or equal to 0 but less than or equal to A over B, and A is greater than 0, B is greater than 0. So the relationship between total revenue and demand for the condition expressed in equation 4 may be represented by the curve shown in this figure. From calculus, the demand D that will produce maximum total revenue can be obtained by solving the DTR and over D is equal to A minus 2BD is equal to 0. So here we are just differentiating the formula. Okay? So you notice this is the total revenue versus the demand. So the formula or the differentiated formula yields this graph. So you notice that it is a bell-shaped graph. So next, thus the demand is equal to A over 2B. So we have derived that formula of demand. Next is 5.6, cost, volume, and break-even point relationships. So fixed costs remain constant over a wide range of activities, but variable costs vary. That's why they are called fixed and variable costs. In total, with the volume of output. Thus, at any demand D, total cost is, so C sub D is the total cost, is equal to C sub F, which is the fixed cost, plus C sub V, which is the variable cost, where C sub F and C sub V denote fixed and variable costs respectively for the linear relationship assumed here. So C sub V, or the cost of variable cost, is equal to C sub U times demand. What is C sub U? So C sub U is the variable cost per unit. So we have a variable cost and we also have a variable cost per unit. So we have a scenario number 1. When total revenue as depicted in the figure and total costs as given in equation 7 and 8 are combined, the typical results as a function of demand are depicted in the figure 2-4. At break-even point D sub 1, total revenue is equal to the total cost. Okay, and an increase in demand will result in the profit of the operation. So that's the formula here means. Okay, so then at optimal demand D, profit is maximized in the equation 10. So at break-even point D sub 2, the total revenue and the total costs are again equal, but additional volume will result in an operating loss instead of profit. So when the total revenue and the total costs are equal, there will be a operating loss instead of profit when additional volume will be produced. So obviously, the conditions for which the break-even and maximum profit occur are our primary interest because that's what we want to find out. So first, at any volume demand D, profit or loss is equal to total revenue minus total cost. So it will be a loss if the total cost is greater than the total revenue. So it is equal to the quantity A times D minus B times D squared minus the quantity C sub F plus C sub U times D. So when we simplify them, we have is equal to negative BD squared plus quantity A minus C sub U times D minus C sub F. So that is our equation number 9. So this is the figure, the combined cost and revenue functions and break-even points as the function of volume and their effect on typical profit. Okay, so you notice here the graph of the total cost and the graph of the variable cost and how they affect the maximum profit or the total revenue. So when the total revenue is above the total cost, it will be a profit. Of course, if it is below, it will be a loss. So we have here a note to guarantee that D maximizes total revenue. Check the second derivative to be sure if it is negative. So this is the second derivative. So it should be negative so that it maximizes the total revenue. Also recall that in cost minimization problems, a positively signed second derivative is necessary to guarantee a minimum value optimal cost solution. So if it is positive, it will yield a minimum value optimal cost solution. Next is, in order for a profit to occur based on the equation 9 and to achieve the typical results depicted in the figure, two conditions must be met. First is, the quantity A minus C sub U must be greater than 0. That is, the price per unit that will result in no demand has to be greater than the variable cost per unit. Okay? So this avoids negative demand because in the equation, if the price per unit will result, if the price per unit is less than the variable cost, it will result in a positive demand. Okay? So remember that. So total revenue or the TR must exceed total cost, okay, for the period involved. So if these conditions are met, we can find the optimal demand at which maximum profit will occur by taking the first derivative of equation 9 with respect to D and setting it equal to 0. So derivative of profit over D is equal to A minus C sub U minus 2BD is equal to 0. Hence, the optimal value of demand that maximizes profit is D minus A A minus C sub U over 2B. That is our equation 10. To ensure that we have maximized profit rather than minimize it, the sign of the second derivative must be negative. Okay? So checking this, we find the second derivative as negative 2b, which will be negative for b greater than 0. So an economic break-even point for an operation occurs when total revenue equals total cost. So if the two become equals, it will be an economic break-even point. Then for total revenue and total cost, as used in the development of the equation 9 and 10, at any demand D, the total revenue is equal to total cost for it to become a break-even point. So using those formula, for the total revenue, it is A multiplied by D minus B multiplied by D squared equals, for total cost is C sub F plus C sub U times D. Then simplifying them or equating them to 0 gives us negative B D squared plus quantity A minus C sub U multiplied by D minus C sub F is equal to 0. So based in this equation 11, because this equation 11 is a quadratic equation, because of the d squared, with one unknown, we can solve for the break-even points d sub 1 and d sub 2, the roots of the equation, using this formula. Okay, so d is equal to the quantity minus the quantity A minus C sub U plus or minus the squared of the quantity A minus C sub U minus 4 multiplied by negative B multiplied by negative C sub F. Right? All raised to 1/2. All over 2 multiplied by negative B. So it used the roots of the equation formula for a quadratic equation. Then, with the conditions for a profit satisfied, the quantity in the brackets of the numerator, or what we call as the discriminant, so this quantity in the bracket, that is the discriminant, will be greater than 0. This will ensure that d sub 1, d sub 2 have real positive and equal values. So that should be, the discriminant should be positive or greater than 0. So now, let's apply those formulas we have to an example. So example 2-1, the optimal demand when demand is a function of price. So what do you mean by that? When demand is a function of price? Meaning, price is dependable to the number of demand. Okay, so a company produces an electronic timing switch that is used in consumer and commercial products. The fixed cost, or C sub F, is $73,000 per month, and the variable cost, or C sub U, is $83 per unit. The selling price per unit is P is equal to $180 minus 0.02 multiplied by demand, because the demand is the function of price here. So based on the equation 2-1, or the equation, so that is the equation 10, okay? You notice here, the equation 10. So for this situation, letter A, determine the optimal volume for this product and confirm that a profit occurs instead of a loss of this demand. So we will compute for the optimal volume, and we will confirm if it is we will confirm that it is a profit instead of a loss. Okay, so we will use the equation 10, which is this. So demand, or the optimal volume, is equal to A minus C sub U all over 2B. So our A here is the intercept of the price axis. So you have your price here. So what is the intercept here? So the intercept is 180. That's why it is 180 here. Minus C sub U, because it is the variable cost, or C sub U. Okay? It is $83. All over 2 times the slope. So what is the slope of the price here? It is 0.02. Okay, so it is equal to 2,425 units per month. Okay, so that is the optimal volume. So let's now confirm if that it is a profit instead of a loss. So we have to question if A minus C sub U is greater than 0. Okay, so is it greater than 0? Yes, it is, because it is $97. Okay, so and is the total revenue minus total cost greater than 0 for D? So it is 2,425 units per month. So here we are confirming. Okay, so now we substitute the values for the total revenue. So this is the formula for it. For the total revenue, we have the intercept of the price, which is 180, multiplied by the volume of the demand, which is 2,425, minus the slope, or letter B, okay, slope of the price, multiplied by the square of the units per month, okay, volume, minus for the total cost. This is the formula. Okay, the fixed cost, which is $73,000, plus the variable cost, which is $83, multiplied by the volume, or the units per month, which is 2,425. So simplifying them, we got $44,612. So as the demand of this volume, 2,425 units per month, results in a maximum profit of $44,612 per month. So it is positive because total revenue is greater than the total cost. So notice that the second derivative is negative. So it is negative 0.04. So we get the second derivative, which is negative 0.04, by just multiplying the exponent 2 to negative 0.02. Okay? Since it is negative, we have ensured that the maximum profit maximizes, or a real profit. Okay? So it's not a loss. It is a demand. So next, for letter B, Find the volumes at which break-even occurs. That is, what is the range of profitable demand? Solve by hand and by spreadsheet. So you can use Excel here. So by solving through hand, you have your equation number 11, equation 11 formula. So total revenue is equal to total cost, the break-even point formula. So this is the formula. Just substitute all the given. For B, it is 0.02, so negative 0.02. So D squared plus, for A, it is $180 minus C sub U, which is $83 multiplied by D, minus C sub F is $73,000 is equal to 0. So simplifying them, you have negative 0.02 D squared plus 97D minus $73,000 is equal to 0. And from by using equation 12, okay, so the equation 12 is this, okay? So D prime is equal to the negative 97 because we are getting root the root of the quadratic equation here. So this is the formula. Negative 97 plus or minus the quantity na 97 squared minus 4 multiplied by negative 0.02 multiplied by negative 70,000 raised to 0.5 all over 2 times negative 0.02. So for this D sub 1, you have, if it is positive, you have 932 units per month. And for the D sub 2, you have 3,918 units per month if it is minus. Okay? Thus, the range of profitable demand for this problem is 932 to 3,918 units per month. Next is scenario 2. When the price per unit or P is for a product or service can be represented more simply as being independent of demand. So here in scenario 2, the price is independent of demand versus being a linear function of demand as assumed in the equation 1 and is greater than the variable cost per unit, C sub U. So a single break-even point results. So then, under the assumption that demand is immediately met, total revenue or TR is equal to P multiplied by D. If the linear relationship for cost in equation 7 and equation 8 is also used in the model, the typical situation is depicted in this figure. Okay? So here, you notice that if the price is independent with the demand, its graph is like this. Okay? So again, it is a profit if the TR or the total revenue is greater than the C sub T or the total cost. Okay? So you have your break-even point here in the intersection. Because beyond that, it will be a loss. You also notice that the break-even point is perpendicular to the fixed cost. So to apply that scenario, in this example 2-5, break-even point when price is independent of demand. Okay, so another scenario here. So an engineering consulting firm measures its output in a standard service hour unit, which is a function of the personal grade levels in the professional staff. The variable cost, C sub U, is $62 per standard service hour. The charge out rate, example selling price, is $85.56 per hour. So the maximum output of the firm is 160,000 hours per year. And its fixed cost is $2,024,000 per year. So for this firm, we will solve letter A. What is the break-even point in standard service hours in percentage of total capacity? So for the solution, we will use the equation 13. Okay? the break-even point equation. So here, we have the total revenue is equal to the total cost. So the profit times the demand is equal to C sub F plus C sub U times the demand. So the demand is equal to C sub F over the quantity of P minus C sub U. So substituting all the given to the equation, we have the C sub F as the $2,024,000 over the price or the profit, because it is the selling price, okay, per hour. It is 85.56 minus $62, which is the variable cost. So it is equal to 85,908 hours per year. Okay? So this is now the break-even point in standard service hours. Now, we will get the percentage of total capacity. So how do we get that? We will just divide the hours per year that we got, okay, the break-even point with the number of hours per year, okay, that the firm is operating. The maximum output of the firm is 160,000 hours per year. Okay, so we divide it. So we have 0.537 or 53.7% of the capacity. Okay, so letter B, what is the percentage reduction in the break-even point? So this is about sensitivity. If fixed costs are reduced by 10%, if variable cost per hour is reduced by 10%, and if the selling price per unit is increased by 10%. So we will find the percentage reduction in break-even point. Utilizing those percentages, okay, for a 10% reduction in C sub F, or the fixed cost, gives this. We just minus 0.1 to 1, okay? So we multiply 0.9 to the fixed cost, and also divide it with the corresponding values in the denominator. Okay, so it is also the equation 13. So next, we will just, we get a 10% here. Okay, 10% reduction just to validate. Okay, so next, a 10% reduction in the demand or the volume. Okay, a 10% reduction in C sub U gives, so we will just multiply the C sub U with 0.9. Okay, so we get 68,011 hours per year, and we just get the percentage of that from this. Okay, the break-even point of the total hours per year. Okay, we will just get the percentage, so it is 0.208. Next, a 20.8 reduction in D. So it is the meaning of that, 20.8%, okay, reduction. So next, a 10% increase in P gives, we will just multiply the price or the intercept of the price with 1.1, because there is an increase of 10%. So we have here this 63,021 hours per year. Now we will just get its percentage through our break-even hours per year. So it is 26.6% reduction in the volume. Thus, the break-even point is more sensitive to a reduction in variable cost per hour than to the same percentage reduction in the fixed cost. Okay, because you notice that when we solve for the reduction in the variable cost, it yields higher reduction. Okay, because here you have 20.8%, okay, while here you only have 10% reduction. So reduction in variable cost is more sensitive, okay. So next, Furthermore, notice that the break-even point in this example is highly sensitive to the selling price per unit, because if the selling price per unit is increased, you notice the higher the reduction in the volume of the demand. Okay. Next, market competition often creates pressure to lower the break-even point of an operation. The lower the break-even point, the less likely that a loss will occur during market fluctuations. Also, if the selling price remains constant or increases, a larger profit will be achieved at any level of operation above the reduced break-even point. So, that is the market competition in real settings, how the market competition operates. Okay? Next, 6.0, cost-driven design optimization.
6.0 Cost-Driven Design Optimization. Since engineers must maintain a life cycle viewpoint as they design products, processes, and services, they should consider a cost-driven design optimization. Because a product or a service that doesn't have a cost-driven design will not have an optimal result. So, this optimization includes simple design models intended to illustrate the importance of cost in the design process. So, this concept shows the procedure for determining an optimal design using cost concepts. Discrete and continuous optimization problems that involve a single design variable. So, we will let the single design variable equals to x. Okay? We will consider as that x in our computation. So this variable is also called a primary cost driver. And knowledge of its behavior may allow a designer to account for a large portion of total cost behavior. So here we will be computing for the single design variable because it is important for a designer because he or she should account for it. For cost-driven design optimization problems, the two main tasks are as follows. So first one is to determine the optimal value for a certain alternatives design variable. For example, what velocity of an aircraft minimizes the total annual cost of owning and operating the aircraft. So that's how we will do it first. We will find the optimal value of an alternative design. Next, select the best alternative, each with its own unique value for the design variable. For example, what insulation thickness is best for a home in Manila? So after we have determined the optimal value for a certain alternative design, we will now select the best alternative among others. So that alternative should have a unique value. So in general, the most models developed in these problems consist of three types of cost. First one is the fixed cost. You already know what it's that. Next is the cost that vary directly with the design variable. So it's a variable cost, and costs that vary indirectly with the design variable. So another variable cost, but this one is indirectly. Okay? So next, a simplified format of a cost model with one design variable is given by this formula. So this formula has a one design variable only. So equation 14. So cost is equal to a x plus b over x plus k. So where a is a parameter that represents the directly varying cost. Okay, so take note of that. Next, b is a parameter that represents the indirectly varying cost. Okay, so while a is directly varying cost, b is indirectly. Next, k is a parameter that represents the fixed cost. Okay, so letter k is our fixed cost there in the formula. Then you X represents the design variable in question. So X will be our design variable. Example of that is weight or velocity. Okay, so in a particular problem, the parameters A, B, and K may actually represent the sum of a group of costs in that category because they should belong in one category, and the design variable may be raised to some power for either directly or indirectly varying cost. Okay, so our design variable, which which is X, can vary. We can raise them to some power. Next, the following steps outline a general approach for optimizing a design with respect to cost. Okay, so here are the steps. Step 1. Identify the design variable that is the primary cost driver. Example, pipe, diameter, or insulation thickness. So, here in step 1, we will identify the specific design variable. Next, step 2, write an expression for the cost model in terms of the design variable. So here in step 2, we will now make our equation. Okay, so equation or expression in terms of the design variable. So it is about making a cost model. Next, step 3, set the first derivative of the cost model with respect to the continuous design variable equal to 0. So first, we will get the derivative. For discrete design variables, compute the value of the cost model for each discrete value over a selected range of potential values. So remember that if it is discrete design variable. Next, step 4, solve the equation found in step 3 for the optimum value of the continuous design variable. For discrete design variables, the optimum value has the minimum cost value found in step 3. Okay, so if it is discrete design, we will select the optimum value, okay, which has the minimum cost. This method is analogous to taking the first derivative for a continuous design variable and setting it equal to 0 to determine an optimal value. Okay, so after we get the derivative for a continuous variable, we should set it to equal to 0 to verify if it is really an optimal variable. And lastly, step 5, for continuous design variables, use the second derivative, okay, of the most model with respect to the design variable to determine whether the optimum value found in step 4 corresponds to a global maximum or minimum. Okay, so if it is continuous design variable, we will get the second derivative. Okay, so now let's apply all those steps in an example. So example 2-6. How fast should the airplane fly? Okay, so here we will be making a decision about that. So the cost of operating a jet-powered commercial passenger-carrying airplane varies as the three halves power of its velocity. Okay, so take note these givens. Next, specifically, C sub 0 is equal to kn v raised to 3 halves, where n is the trip length in miles, k is a constant of proportionality, and v is velocity in miles per hour. It is known that at 400 miles per hour, the average cost of operation is $300 per mile. The company that owns the aircraft wants to minimize the cost of the operation. Of course, every company wants to minimize the cost of their operation, but that cost must be balanced against the cost of the passenger's time. So, it should be balanced. Why? Because the customer satisfaction also matters. So, which has been set at $300,000 per hour. So, these are the questions that we are going to answer. Letter A question, at what velocity should the trip be planned to minimize the total cost? which is the sum of the cost of operating the airplane and the cost of passengers' time. So here in letter A, we are going to find the optimal trip that is to be planned. Okay, so letter A, the equation for total cost is of course the summation of the cost mentioned. So C sub t is equal to C sub 0 or C sub O plus C sub C is equal to K and V raised to 3 halves. So C sub 0 is this, K and V raised to 3 halves, while C sub C is this, plus $300,000 per hour. So N over V. So N over V has uh, time in hours as its units. So first, we will solve the value of K before we solve this. Okay, so to solve the value of K, we will just use this formula. Okay, where C sub 0 is the $300 or the average cost of operation per mile. That's why it is $300 over mile. Okay, equals K. So K here is the variable we are trying to solve, while V is the velocity. It is 400 miles per hour given here. Okay, so it is raised to 3 halves. So just dividing both sides by 400 miles per hour raised to 3 halves, we now get this. Okay, we first distribute the exponent 3 halves. So 400 raised to 3 halves is 8,000. Then miles raised to 3 halves, then hours raised to 3 halves. Okay, so now we can divide 300 by 8,000. It is $0.0375. Hours raised to 3 halves over miles raised to 5 halves, because we will divide or multiply. Okay, multiply the mile with miles raised to 3 halves. That's equal to miles raised to 5 halves. Thus the total cost is equal to, we will now just substitute what we got from the previous equation. So this K we will just substitute here. Okay, because in the first equation uh, the total cost is equal to K and V raised to 3 halves. So we have now our K. So we'll just substitute that here, and N miles, V miles per hour. And in the equation, it is raised to 3 halves plus 300,000 per hour. So what is that? Is 300,000 per hour. So it is the C sub C, or the cost of the passenger's time. So N miles over the velocity miles per hour. So we will just simplify them. We now multiply all of this together. Then we add, we also multiply this to this side. Then we add them together. So since they don't the same variable, we cannot add them. So next, the first derivative is taken here. So to get the derivative of this first term, okay, we just bring down 3 halves. Okay, then minus 1 to the exponent of 3 halves. That becomes 1 half. Now, for this term here, we will just use the fractional derivative. Okay, so you recall how to get the fractional derivative, because this is a fraction. Okay, so it will be minus $300,000 and over v squared is equal to 0. Okay, So next, just multiply 3 halves by the quantity here. It will become 0.0562 v raised to 1 half minus 300,000 over v squared equals 0. Now, next, we now multiply both sides by v squared to eliminate it. That's why the first term has now 5 halves in the exponent, while the second term becomes 300,000 only. Next, we'll just transpose 300,000 to the other side of the equation, then divide both sides by the coefficient of the variable here. For the v raised to 5 halves, be left in this side of equation only. So if we divide it, we will have 5,333,333. So we'll just get the next we will just raise both sides by 2/5. So 5 halves here is cancelled. Now 2/5 is equal to 0.4. So 5,333,333 raised to 0.4 is equal to 490.68 miles per hour. So now we got the velocity that the trip should be planned, okay, to minimize the total cost. Next, letter B. How do you know that your answer for the problem in part A minimizes the total cost? So here we will just check it. To check it, we will just get the second derivative to confirm a minimum cost solution. So we'll get the second derivative of this equation, okay? That is the first derivative. So c sub t over v squared, because it is already the first derivative. So getting the second derivative, the first derivative, we will just bring down the 1 half. So we will divide 0.05625 with 2. That's why it is 0.028125 here. Then the 1 half will be minus with 1. That's why it is bring down here, because it will be negative. Okay? Then using the fractional derivative again, okay, you have this, it will be positive 600,000 over v cubed. So if we assume that v is greater than 0, then the second derivative will be greater than 0 also. So if that happens, we have our minimum cost solution. So the company concludes that the velocity of 490.68 miles per hour minimizes the total cost of this particular airplane's flight. So another problem, example 2-7. This is about energy savings through increased insulation. So this example deals with the discrete optimization problem. So the previous problem is continuous because velocity is a continuous variable. So now this problem is about discrete, okay, of determining the most economical amount of attic insulation for a large single-story home in Virginia. So it's about making an attic insulation. So in general, the heat lost through the roof of a single-story home is given by this equation. So heat loss in BTU per hour. So BTU is an abbreviation for British Thermal Unit. It's equal to delta temperature. When you see a delta, it means there is a change, okay? Change in temperature in degrees Fahrenheit, multiplied by the area in feet squared, then multiply by the conductance in BTU per hour over all over feet squared minus degrees Fahrenheit. So this equation represents the relationship here. So Q The heat loss is equal to the temperature inside minus temperature outside multiplied by the area and the conductance. Okay, U. So in Southwest Virginia, the number of heating days per year is approximately 230, and the annual heating degree days equals 230 multiplied by the difference of 65 degree Fahrenheit and 46 degrees Fahrenheit, which is equal to 4,370 degrees Fahrenheit per year. So here, 65 degree Fahrenheit is assumed to be the average inside temperature, while 46 degrees Fahrenheit is the average outside temperature each day. So consider a 2,400 feet squared single-story house in Blacksburg. So it is also in the Southwest Virginia. Okay, so the typical annual space heating load for this size of house is 100 times 10 raised to 6 BTU. So that is, with no insulation in the attic, we lose about 100 times 10 raised to 6 BTU per year. So common sense dictates that no insulation alternative is not attractive and is to be avoided, because with insulation in the attic, the amount of heat loss each year will be reduced. So the value of energy savings that results from adding insulation and reducing heat loss is dependent on what type of residential heating furnace is installed. Because in their country, it is very cold. That's why the uh, insulation to conserve heat is important. So for this example, we assume that an electrical resistance furnace is installed by the builder, and its efficiency is near 100%. So now we're in a position to answer the following question: what amount of insulation is most economical? And additional piece of data we need involves the cost of electricity, which is $0.074 per kilowatt hour. This can be converted to dollars per 10 raised to 6 BTU as follows. Okay, so 1 kilowatt per hour is equal to 3,413 BTU. So to convert that furthermore, we have 293 kilowatt per hour in BTU. So there is 293 kilowatt hour per million BTU, because when you multiply 293 and 3,413, it will be equal to million BTU. So this is the computation, how it is arrived here, that how does the problem arrive in this computation. So here, 100 times 10 raised to 6 BTU per year is approximately equals to this, 4,370 days per year over 1.0 efficiency. So this value is from the problem. Okay, it is the degrees Fahrenheit days per year, while this 1.0 efficiency is equal to the efficiency 100%. Okay, that's why it is 1 here. So in the problem, it is given that 2,400 feet squared, the area. Okay, so the area is here. So remember the formula. Okay, this formula. So we are using this formula. Okay, then multiply by 24 hours per day, and this, the conductance, multiply by the conductance, where 0.397 is the U factor, or the conductance factor, with no insulation. So simplifying them, we got this. It is approximately $21.75 over 10 raised to 6 BTU. So the cost of several insulation alternatives and associated space heating loads for this house are given in the following table. So an R value indicates the resistance to heat transfer. The higher the number, the less the heat transfer, because it is resistance. So in view of this data, which amount of attic insulation is most economical? The life of the insulation is estimated to be 25 years. So here, in order for us to get the cost of heat loss per year, we will just multiply, okay, $21.75 over 10 raised to 6 BTU by this corresponding annual heating load BTU per year. So 21.75 multiplied by 74, the 10 raised to 6 will be cancelled. Okay, so the answer will be 1609.50. So you will do the same for the rest. Okay, now for the cost of heat loss over 25 years, you will just multiply this, the cost you got in letter B with 25 because this is yearly, okay, in letter B. Then in letter C, over 25 years, so we will multiply by 25. So this is the answer. So 1609.5 multiplied by 25 is equal to this, 40,237.50. Then you will do the same to the others. Now to get the total life cycle cost, we will just add the investment cost plus the cost of heat loss over 25 years because it is what makes the total life cycle cost. Okay, so adding them $600 plus 40,237.50, it is $40,837.50. So you will just do the same for the rest. And now you notice that R38 yields the lowest. That's why the answer here is to minimize the total life cycle cost. Select R38 insulation because it has the lowest or minimal total life cycle cost. So caution, this conclusion may change when we consider the time value of money. Okay, an interest rate greater than 0 in the next chapter we will be discussing it. In such a case, it will not necessarily be true that adding more and more situation in the optimal course of an action. So you will be learning that in the next chapter. Next is 7.0. Present economic studies. When alternatives for accomplishing a specific task are being compared over 1 year or less and the influence of time and money can be ignored, engineering economic analysis are referred to as present economic studies. Okay, so we call it about the present economic studies. So the following rules are used to select the preferred alternative when defect-free output or the yield is variable or constant among the alternatives being considered. Okay, so this is the rule of 1. When revenues and other economic benefits are present and vary among alternatives, choose the alternative that maximizes overall profitability. Okay, because that's what we want. What we want. Higher profit means more money for the company. So based on the number of defect-free units of a product or service produced. So profitability must be based on the products that don't have defect. Okay, because if a product has a defect or a service is not good, then it is a cost to the company. So rule number 2, when revenues and other economic benefits are not present or are constant among all alternatives, consider only the cost and select the alternative that minimizes total costs per defect-free unit of product or service output. So, while rule number 1 is about the profit, high profit, rule number 2 is about the cost. We will select the lowest cost. 7.1 Total cost in material selection. In many cases, economic selection among materials can be based solely on the cost of materials. So why? Because Frequently, a change in materials will affect the design and processing cost, and shipping cost may be altered. So all those costs may vary over the uh, the process, the processing of materials. So example of 2-8, choosing the most economic material for a part. So a good example of this situation is illustrated by a part for which annual demand is 100,000 units. So you take note of that. Annual demand is equal to 100,000 units. The part is produced on a high-speed Torre lathe. So what is a Torre lathe? So it is a machine used to shape metals, okay, to get the desired sizes or specification. So using 1112 screw machine steel costing 0.30 per pound. Okay, so those are the cost of materials when you are using the high-speed Tourette lathe. So a study was conducted to determine whether it might be cheaper to use brass screw stock, okay? Because it cost $1.40 per pound. Because the weight of the steel required per piece was 0.0353 pounds and that a brass was 0.384 pounds, the material cost per piece was $0.0106 for steel and $0.0538 per brass. So you take note of all those given. However, when the manufacturing engineering department was consulted, it was found although 57.1 defect-free parts per hour were being produced by using steel, the output would be 102.9 defect-free parts per hour if brass were used. So the engineering department found out that when the operation is using brass, they will have a 102.9 defect-free parts. Okay, so which material would be used for this part? So we will now weigh their advantages. So the solution, the machine attendant is paid $15 per hour, so another variable here. And the variable traceable overhead costs for the Torre lathe are estimated to be $10 per hour. So we have also a overhead cost here. So thus, the total cost comparison for the two materials is as follow. We will just put them in a comparison table. So first, this column is about the 1112 steel and this column is about the brass. So for the material, the cost is $0.30 times 0.0353 is equal to $0.0106 for the steel. While in brass, it is 0.0538. Okay? So in the, labor, we will just divide $15. So why $15? $15 is divided by 57.1 here because we are getting the cost per piece because we have 57.1 defect-free parts, okay, for steel. That's why we are dividing it. We are getting the cost per piece under the labor. Okay, the same with under the brass. $15 is divided with 102.9 defect-free parts. Okay, so next, the variable overhead, $10 per hour is divided also with the parts. So it is important to divide the cost with the total number of parts because we are considering the cost per part here. Okay, so next, the total cost per piece. That's the reason why we divide them because we are getting the total cost per piece. So for steel is $0.4484, while for brass it is 0.2968. So saving per piece of by use of brass. So how much we save by using brass? We just subtract, okay, the total cost per piece of steel with the total cost per piece of brass. So it is now $0.1516. Okay, so that is the saving per piece. So that's how much the company will save using brass. So because 100,000 parts are made each year, revenues are constant across the alternatives because it is the same output. Okay, so rule 2 would select brass, and its use will produce a savings of what? We will just multiply it with the number of parts. That's why we got 151.60 per thousand. So a total of 15,160 for the year. So we got 151.6 here because we multiply it by 1,000. That's why it is per thousand. But if we multiply it by 100,000, we will get $15,160 savings per year. Okay, so it is also clear that the costs other than the cost of material, such as labor and overhead, were important in the study. So why? Because they also contribute to the computation of the cost. Okay, so care should be taken in making economic selection between materials to ensure that any differences in shipping cost, yields, or resulting scrap are taken into account. Okay, because we will be adding those costs. There are costs in shipping, okay, in yields if the product are defective, as well as in the scrap, because when the product becomes a scrap, the uh, the work that will be done to it will be a cost to the company. Okay, so they are all the costs should be taken into account. So commonly, alternative materials do not come in the same stock sizes, such as sheet sizes and bar lengths. Of course, because different materials, different sizes. This may considerably affect the yield obtained from a given weight of material. Similarly, the result scrap may differ for various materials, so we need to classify them. In addition to deciding what material a product should be made of, there are often alternative methods or machines that can be used to produce the product, which in turn can impact processing cost. So it is true because when a product is made from a machine, it is different from a product that is made from the worker's hand. Okay? So processing times may vary with machine selected, as may the product yield, because machines produce more than the hands of people, okay? Or the manual work. So as illustrated in the next example, these considerations can have the important economic applications. So another example problem: choosing the most economical machine for production. So, two currently owned machines are being considered for the production of a part. The capital investment associated with the machines is about the same and can be ignored for purpose of this example. So, investment will be ignored here. The important differences between the machines are their production capacities, production rate, multiplied by available production hours. So that's how we get the production capacity. And their reject rates by percentage of parts produced that cannot be sold. Okay? Because they are reject or defective. So consider the following table. For machine A, the production rate is 100 parts per hour, while in machine B, the production rate is 130 parts per hour. Next, hours available for production under machine A is 7 hours a day, while in machine B is 6 hours a day. So the percent of parts rejected for machine A is 3%, while in machine B it is 10%. So the material cost is $6 per part. So it is given, okay? And all defect-free parts produced can be sold for $12 each. So the rejected parts have negligible scrap value. For either machine, the operator cost is $15 per hour, and the variable overhead rate for traceable cost is $5 per hour. So it is for both machines. So these are the questions we are going to answer.
Letter A. Assume that the daily demand for this part is large enough that all defect-free parts can be solved. Which machine should be selected? So, for letter A, we will consider rule 1. So, it applies in this situation because total daily revenues, or the selling price per part, times the number of parts sold per day, and total daily cost will vary depending on the machine chosen. Okay, because they have different capacities. Therefore, we should select the machine that will maximize the profit per day.
So, profit per day is equal to revenue per day minus cost per day. Under revenue per day, they are production rate multiplied by the production hours multiplied by the profits, $12 per part, times 1 minus the quantity of percent reject over 100. Because here we are subtracting the reject, because the company does not profit from the reject. So minus, these are the costs per day, minus the production rate multiplied by the production hours, and $6 per part is the material cost, minus also the production hours multiplied by $15 per hour. So this is the operator cost, plus $5 per hour the overhead rate. Okay, so for machine A, profit per day is equal to 100 parts per hour, 7 hours per day, multiplied by $12 per part. Multiply by this, 1 minus 0.03, because 0.03 is the percent of reject. Okay, then these are the cost. So for machine A, the profit per day is equal to 3,808 per day dollars per day. Okay, so that is the profit. For profit machine B, the profit per day is this, 3,624 per day. So therefore, select machine A because it has a higher profit. It maximizes the profit per day. Next, letter B. So for letter B, what would be the percent of parts rejected have to be for machine B to be as profitable as machine A? Okay, so we will compute the percent of parts rejected in machine B so that they are the same as profitable as machine A. So for the solution, to find the break-even percent of parts rejected, so X for machine B, so we will set the percent parts rejected because equals to X because we do not know that quantity. So set the profit per day of machine A equal to the profit per day of machine B and solve for X. Okay, so we will set the profit per day of, so this is the profit per day of machine A. We will set it equals to the computation of profit per day of machine B, and it is the same with the computation in the previous example. Okay, but here we let X be equal to the percent of parts rejected. So solving that, we get X as, so simplifying that, we get X as 0.08. So the percent of parts rejected for machine B can be no higher than 8% for it to be as profitable as machine A. Okay. 7.2, making versus purchasing or outsourcing studies. So in short run, say 1 year or less, a company may consider producing an item in-house even though the item can be purchased or outsourced from a supplier at a lower price than the company's standard production cost. So this could occur if indirect and overhead costs are incurred regardless of whether the item is purchased from an outside supplier. So it will be the same. That's why a company may decide to just make the part that is needed or the item that is needed in their own setup or in their own company. Next, the incremental cost of producing an item in short run is less than the supplier's price. Therefore, the relevant short run cost of make versus purchase decision are the incremental cost incurred and the opportunity cost of the resources involved. So because if a company will purchase an item to another company or supplier, it might cost much, okay, than producing it in their own. So that's the incremental cost. If the incremental cost is higher when purchasing from other company, then it is better to do the item in the company itself. Next, opportunity cost may become significant when in-house manufacture of an item causes other production opportunities to be foregone, often because of insufficient capacity. So that is opportunity cost. That is, it is referred to the opportunity lost when a company is making a product other than the products that they are supposed to do. Okay, because they are making the additional products, opportunity cost will be incurred because the opportunity of making the regular product will be lost. But in the long run, capital investments in additional manufacturing plant and capacity are often feasible alternatives to outsourcing. Okay, so they are better than uh, outsourcing or buying from other companies because engineering economy often deals with changes to existing operations. Standard cost may not be too useful in make versus purchase studies. So in fact, they are used. Standard cost can lead to an economically decision. So we will avoid using a standard cost. So example 2-10 illustrates the correct procedure to follow in performing make versus purchase studies based on the incremental cost. So this example will show us how to decide in making an item or just purchasing that item. Okay, so to produce or not to produce, that is the question. So a manufacturing plant consists of three departments, A, B, and C. So Department A occupies 100 square meters in one corner of the plant. Product X is one of the several products being produced in Department A. The daily production of Products X is 576 pieces. The cost accounting records show the following average daily production cost for Products X. So here are the costs for Product X. The direct labor, one operator working 4 hours per day at $22.50 per hour, including fringe benefits plus a part-time foreman at $30 per day. So it has a total of $120. Next is the direct material, which cost $86.40. And last is the overhead cost, which cost at $0.82 per square meter of floor area. So since there is a 100 square meters, 100 multiplied by 0.82 is equal to 82. So the total cost per day for Department A in making the product X is, you will just add all of them, it is $288.4. So the department foreman has recently learned about an outside company that sells product X. Okay, so there is a company that sells the same product that the former company is doing or making. So that another company makes the product X at $0.35 per piece. Accordingly, the foreman figured a cost per day of $0.35 multiplied by 576 because 576 is the pieces of product X to be produced. That is why the cost per piece is multiplied to it. So it is equal to $201.60. So resulting in a daily savings of, so we will just subtract the total cost per day in Department A with the cost that is associated with buying the the products X to the other company, which is 201.6. So subtracting them, a daily saving of $86.80. So therefore, a proposal was submitted to the plant manager for shutting down the production line of product X and buying it from outside company. So, however, after examining each component separately, the plant manager decided not to accept the foreman's proposal based on the unit cost of product X. So, why? First consideration is the direct labor. Because the foreman was supervising the manufacture of other products in Department A, in addition to product X, so there are more products other than products X in Department A. And the foreman is also assigned in monitoring them. So the only possible savings in labor would occur if the operator working 4 hours per day on product X were not assigned after this line is shut down. So the working hours that is supposedly to be done for product X should be assigned to other. So that is a maximum savings of $90 per day would result. Okay, so that will be the savings if the company refrain from doing products X. So next, number 2, materials. The maximum savings on direct material will be $86.40 because that is what we got from when we subtract them. Okay, the cost in making the product in the company and the cost of making the product in other company. So however, the figure could be lower if some of the material for products X is obtained from scrap of another product. Okay, so we can consider that also if we can use the reworks or the scraps from other products, then the cost of the material will be lessened. So next, overhead. Because of other products are made in Department A, no reduction in total floor space requirements will probably occur. So therefore, no reduction in overhead costs will result from discontinuing products X. So there will be no effect when in the overhead cost when the company stops doing products X. It has been estimated that there will be daily savings in the variable overhead cost traceable to products X. Rather, there is a saving, and it is $3 due to the reduction in power, okay, cost, and in insurance premiums. So, for the solution, if the manufacturer of products X is discontinued, the firm will save at most $90 in direct labor. Why it is $90? Because it is given in consideration number 1, direct labor. Okay? So how do we get $90 there? We just multiply 22.50 with 4 hours. Okay? So next, the $86.4 in direct material, so it is given there. We have computed it, and the given $3 in variable overhead cost. So we will just add all of them. It totals $179.40 savings per day. Okay, so this is estimate of actual cost savings per day is less than the potential savings indicated by the cost accounting records, which is 288.40 per day. So it is less than with the accounting record. So it would not exceed $201.60 to be paid to the outside company. Okay, because it 201.6 is the cost in buying or outsourcing the item to the other company. So if products X is purchased, for this reason, the plant manager used Rule 2 and reject the proposal of the foreman and continued the manufacture of products X. So this is the Rule 2. Okay, remember, the incremental cost of producing an item in the short run is less than the supplier's price. So it is true. Because the incremental cost computed is 179.40 per day, while the cost is 201.6 when the item is bought from the other company. Okay, so in conclusion, example 2-1 shows how an erroneous decision might be made by using the unit cost of products X. Okay, because in the accounting records they use the the unit cost, okay, of products X. That's why they arrive in 288.40 per day. Okay, so that will result in erroneous or mistake. Okay, so the fixed cost portion of products X unit cost, which is present even in the manufacture of products X, is discontinued, was not properly accounted for in the original analysis by the foreman. So that is uh, uh, the neg- uh, the part that is neglected by the foreman when he is computing or when he is making his analysis. Next, 8.0 trade-offs in energy efficiency studies. So energy efficiency affects the annual expense of operating an electrical device, such as a pump or motor. So it is true because uh, a device can consume more energy, okay, if it is used for higher volume production. So it affects the operating cost. So typically, a more energy efficient device requires a higher capital investment than does a less energy efficient device. But the extra capital investment usually produces annual savings in electrical power expenses relative to a second pump or motor that is less energy efficient. This section explains how the annual expense of operating an electrical device is calculated and traded off against capital investment cost. So here we will learn how to decide if we are going uh, to choose a less expensive yet less energy efficient device or a much more expensive but a higher energy efficient device. So if an electric pump, for example, can deliver a given horsepower or kilowatt rating to an industrial application, the input energy requirement is determined by dividing the given output by the energy efficiency of the device. The input requirement in horsepower or kilowatt is then multiplied by the annual hours that the device operates and the unit cost of electric power. Okay, so you can see that the higher the efficiency of the pump, the lower the annual cost of operating the device is relative to another less efficient pump. Okay, so that is true because when the device is when the device has a higher efficiency, he will consume less uh, less energy. Okay, that will entail less cost. So this example 2-11 will show us how to decide if we are going to invest in electrical efficiency devices. Okay, so two pumps capable of delivering 100 horsepower to an agricultural application are being evaluated in the present economy study. So the selected pump will only be utilized for 1 year and it will have no market value at the end of the year. Pertinent data are summarized as follows. So for the first pump, which is the ABC pump, the purchase price is $2,900. For the XYZ pump, the purchase price is $6,200. And for the maintenance cost of ABC, $170 and $510 for XYZ. Then last is efficiency of ABC is 80% while 90% of XYZ. So, in electric power cost, $0.10 per kilowatt and the pump will be operated 4,000 hours per year. Which pump should be chosen? Recall that 1 horsepower is equal to 0.746 kilowatts. Okay, so we will decide which pump is more economically. So for the solution, the expense of electric power for ABC pump is written here. Okay, so we will put them one by one. First is for ABC pump, 100 horsepower over 0.8 because it is the efficiency. We will divide it, then multiply by the kilowatts hour per horsepower because it is equal 1 horsepower is equal to 0.746 kilowatts per hour. Okay, then we will multiply by the cost per kilowatt per hour. Okay, the 0.10 dollars. So it is the electric cost. Then multiply by the total hours, which is 4,000 hours per year. So we have $37,300. That is the expense of electric power for the first pump, which is ABC pump. Now, next for second pump. For the second pump, XYZ pump, here is the expense of electric power. So first, the horsepower or the capability is just the same with the first pump, which is 100 horsepower. Then we'll just divide it with the efficiency, 0.9, because it is 90%. Then we will multiply it with 0.746 kilowatt hour per horsepower to convert it. Okay, because the first unit here is horsepower. Okay, in our problem, there is a conversion because our power cost is in dollars per kilowatts. That's why we convert it. Okay, so the same cost, electric power cost, $0.10, then multiply with the same operating hours. So it is equal to $33,156. So thus, the total cost of owning and operating the ABC pump is 40,370. So how do we get 40,370? We just add the expense of electric power that we got from ABC power pump with the purchase price and the maintenance cost. Okay? So the same with the XYZ pump. We just add the expense of electric power that we got, which is 33,156 with its purchase price and maintenance cost. So it will result to 39,866. So consequently, the more energy efficient XYZ pump. So it is more energy efficient because the cost of it per year is lower than the ABC pump. It should be selected. So XYZ should be selected. To minimize the total cost, notice the difference in energy expense is $4,144. So how do we get this 4,144? We just get the difference, okay, of 33,156, which is XYZ pump, and the 37,300, okay, because the XYZ pump has a 90% efficiency while the ABC has only 80% efficiency. This cost reduction more than balances the extra 3,300 in capital investment. So the 3,300 is from subtracting 6,200 with 2,900. Okay, because it is said here that the investment cost, the additional investment cost, 3,300 when you buy XYZ pump will be offset by the savings. Okay, because the savings is much higher, and $340 in maintenance required for the XYZ pump. So we get $340 by subtracting 170 from 510. Okay, so all this cost will be offset by the higher savings. So the decision here is to choose XYZ pump. So for your post test, you will answer numbers, the remaining numbers. Okay, numbers 8 onwards. Okay, numbers 8 to letter B. Okay,